So this is joint work with my colleague Hui-King Lee, who's been developing this work with me for about seven years or so. So I wanted to start by telling you a bit about what Wrangler is. And then, I mean, not to overstate it, but first of all, it's a tool. It's a tool for doing refactoring, and I'll show you some of that a bit later on. And it lives inside Emacs and Erlang IDE. But it's not just that. So another way of seeing it is that it's a toolkit. So we provide you with certain facilities, and you can use those as you wish yourselves. So, for example, you can use it from the Erlang shell. You don't have to use it inside Erlang IDE or Emacs. And we've got an open API for you to define new refactorings. And we've got a domain-specific language for scripting, well, scripting sort of on steroids, for scripting more complex refactorings. So you don't just have to use what comes out of the box, you don't even have to use the box, as it were. And I'll show an example of that using, of how you can migrate from one API to another. We've done some work in the past of migrating from regexp to RE, which is the old and the new regular expression libraries for Erlang. But what I'm going to do today is show you how you can migrate to maps, which are in release 17 from dict. Okay, but as well as being a tool kit, it's a tool set. So in the box, as well as the tool itself, are some other tools for doing things like clone detection, detecting module bad smells, and it also interoperates with other tools like QuickCheck and eUnit, so that it plays properly with those. It doesn't allow you to refactor your tests in a way that will break the conventions of a particular testing framework. And it's sort of a laboratory for trying out new things. So I have some students at the moment working on using the rewriting facilities of Wrangler to build a symbolic evaluation tool, partly for teaching, partly for doing refactorings on top of that. And we've been playing around with slicing and doing some concurrency refactorings as well. So there's a whole lot of things out there in the box. So let me show you some of those. But first of all, I realized that not everybody knows why Wrangler is called Wrangler, so I thought I would just explain that. It's an Erlang tool, so it does refactoring. So we could have called it Erlang or Erlang, but we sort of refactored things a bit and came up with Wrangler. So it's an anagram of Erlang refactorer. But also, a Wrangler is somebody who does long and complicated things. It's also somebody who's good at doing mathematical manipulations. So we thought it was a nice name. So just to set the scene there. So Wrangler is a tool. What we do in refactoring is we change how a program works without changing what it does. And it's part of a programmer's standard toolkit. Well, that's what we intend. And some of the things that typically you do in a refactoring tool are things like renaming functions, variables, modules, or whatever, extracting functions from sections of code, or generalizing a function you already have. And I've put those up there because those are the things that people use the most, not just if you're doing refactoring in Erlang, but if you do OO refactoring. Those are the things that tools get used for. Why do we build a tool? Well, the phrase is, it avoids the tedious and error-prone. If you've got a large project and you want to rename a module, then every function call to a function in that module has to change. If you rename simply a function, then every call to that function across the project has to change. So what we do is implement the simple refactorings like renaming, but get all the tedious bureaucracy right. So we cover the whole language. In the case of Erlang, we cover the whole project, and we play properly with tests. So I was going to do a number of little demos as we run through this. So let me start off by. So you're going to see this inside. This is Aquamax. Can you read it at the back? Is everything visible? A little bigger. Ooh, I can. If you insist. You don't really need to read what the words say, but anyway, what was I going to look at? I was going to look at this one, right, okay. So what have we got here? We've got a simple, something I pinched off Francesco. It's a simple ping pong program. But let me just show you the sort of thing we can do I can rename this function here. We've got a menu called Wrangler. I go to refactor, and this is a collection of refactorings that we've got. And let's rename this function. It's called init A. Let's call it start A, just for the sake of argument. So we need to rename the function, and what will it do? It allows us to preview, but let's just commit the change. And you can see that it's changed the name of the function, but it's also changed the name in the export list and changed the spawn there. Because that atom, the use of that atom there, we're clever enough to figure out that that's actually, it's not just the atom init A, it's the atom being used as the name of that function. So we can undo that. You can always undo. And I hope that sends everything back to where it was. So that's an example of, renaming, but we can do function extraction. So we select some code. We think we'd like that to be a function. Let's call it something like, what should we call it? Function. That should be all right, and let's commit that. And then what you can see is that we've extracted the function out there, and we've replaced the code that the original call was to by call to function. And then finally, what we might want to do, this is doing a number of things by hand, but what we might want to do is think, actually, that function, I'm not particularly bothered about that message being in there. I'd quite like to generalize over that, so I can call it with a different message. And that's one of the standard refactorings we've got is we give a new name here. Let's call it MSG. Oops, it failed. Why did it fail? Because we've already got something called MSG. So let's do that again. And what we should see is, whoa, what am I doing? Generalize. Let's call it string. And commit. And then you see what we've done is we've now got a 3-argument version of that function. And it's passed in that extra argument there. Okay, so we can we can undo those things just in case we decided we didn't want to do that. And we've got those. We can go back to the status quo as it was before. So that's the simple sort of refactorings that we can do inside the tool. Now let's go back to the talk. So what we've seen is renaming and function extraction and generalization. So what can we do with Wrangler as a toolkit? Well, it's written in Erlang. It's just an Erlang application, so you can extend it yourself. So, situation like that. But what we've tried to do is tidy things up a bit, so we present a nicer view of the internals to the world, that is you, so that you can extend it more easily. And the key idea is that I think if you search for image of Erlang, this is what you get, or Erlang people. There might be some people in the audience, I don't know. I don't know what Elizabeth Taylor is doing up there, but anyway, she's clearly an early adopter of Erlang. You know Erlang, so the assumption is you know that, but you don't really care about learning a whole new language for manipulating Erlang code. You don't particularly want to learn what the syntax tree is like. So what we want to do is provide you with an abstraction layer that makes dealing with Erlang programs that much easier. So what we've done is provide two things, and these are complementary. We've provided an API that allows you from scratch to define new refactorings. So you can use Erlang concrete syntax to say, I want to turn this sort of thing in Erlang into that sort of thing. Now, this is for refactorings, but you can actually use this for doing more thoroughgoing transformations. In that sense, it's quite like the work that Ricard Carlson has been doing with Merle. I think ours is a bit more cheap and cheerful, probably not as general, I think, but it allows us to do a lot of the work that we want to do. So we've got the API. We spent a lot of time thinking, well, we should be able to just do one thing, but realized, in fact, there were two quite separate tasks going on here. One was to define new refactorings from scratch. The other was for putting together existing refactorings in new and different ways. And what we've done there is build a little domain-specific language. I'll talk about that a bit later on. And that's embedded itself in Erlang. So you can use Erlang in working with that DSL. So what have we got in the API? What sort of things were we asked to do? Typical cases that people say, oh, we wish you could implement this sort of thing. You have somebody working on your project. They've contributed really nice code to your project, but they use the wrong sort of naming. They build their names like this with a capital letter instead of the good old-fashioned Erlang way of having an underscore. You've got a whole lot of things you want to convert in that way. We can easily do that for you. Batch naming batch renaming of modules. We did some work for Qvik of transforming their property-based testing models in a particular way. They had them instrumented, and they didn't want the instrumentation in what they shipped. So we put together a refactoring that supported that. And also this API migration, which I talked about. So what does the API look like? Well, it's worth thinking a bit about what happens when you do something like generalization. Because if we do that, it's then clear what we need to do in order to build the API. So here we've got an example of we generalize a function. It was the example I showed you earlier, in fact, where we generalize over that string ping. What do we have to do in order effectively to describe that implementation? We have to be able to describe expressions, and we have to be able to describe what they are transformed to. So we have to be able to say, take a pattern like this, turn it into a pattern like this. So we need to be able to describe fragments of the concrete syntax, or fragments of syntax using Erlang concrete syntax. But in order to make sense of this, we're not just doing rewriting, we're not doing search and replace, we have to do more than that. We have to think about the context and the scope. There might be a whole lot of other modules sitting out there, so we have to be able to describe the context of what we're doing. And we also have to be able to do things like a check here. If I said I want to generalize this function over that expression, I'd like the refactoring tool to say, no, you can't, because that involves a variable it's a free variable, effectively. So we need to be able to check preconditions of these transformations. So we need to be able to describe bits of syntax, get transformed to other bits of syntax in this context with certain conditions being satisfied. So we can't generalize over an expression with free variables or use the same name as an existing variable. So we need to know variables in scope. We need to know a number of things like that. So we have to put that sort of information somewhere available in our API. And so the way the API looks, if we build it up, is we have templates, bits of Erlang concrete syntax involving variables that range over expressions, what you might call meta variables, describing expressions. We've got rules that describe transformations, turn this into this, context for describing preconditions, and we also supply traversals to say how a transformation should be applied. Should it be applied to a whole tree, or just a portion of a tree, or all the trees that belong to a whole project? We can describe that. So the scenario I wanted to talk about was maps are in R17 as somewhat experimental, but one thing we might want to ask is, can we use maps in our project? Can we take a project, for example, that uses dict and turn that into a project using maps? Well, the question we can ask is, are there any non-map-like uses of dict in our project? Because there are some things maps don't give you the same interface as dictionaries. And so what I've got here is a little piece of code from our library. You can see it's running top down, it's traversing the whole of our project. It's collecting things of this form, where you have a function. These are meta variables. They're actually Erlang variables. You can put these in, but we treat them as meta variables. It's a function applied to some arguments. And we want to check that the function definition info for that function is whether it's in this list that we've put together of the things that are non-map-like. I mean, this is obviously we had to write this. we've examined the API, and we do it over these particular search paths. So that tells us that will search a whole project. So that's what we can do. And if you do this on say, RabbitMQ server, we took that today as an example, we get these code fragments. So let's go to that, and let's try it live. It's always a bit scarier doing it live. Ooh, oh no! I thought I'd switched everything off. Bloody Java. Right, okay. What do I want to do? That really. So inspec examples. So this is a code. We've got a module which has some code inspection functionality, and we want to find. We've written this already. It's just got the code. Find non-map like dict. It's this. Something funny with it. Let me close that. And if we try it again, I don't know why it does that. Okay, so now it's checking the whole of this RabbitMQ server, and if I turn on, sorry, this is a bit compile mode. Oh, what? Compiler. Sorry, this is compilation. Thank you. I'm getting off my compilation mode. It's done. Help. It should be in here. Right, okay. Calm down. Escape X. There we are. So the nice thing about Emacs, it will give you live links in here. So I can now click on these, and this will take us to where, if I just turn the size of that down a tiny bit, you can see here we've got a dict merge usage. So we can look across our project and see that we've got 10 places where we might have some problems. We have about 170 uses of dictionary, which are fine. So the chances are it would be reasonably easier for us to migrate our use of dictionary to a use of map if we can sort out those particular fragments. So, and we just wrote that. It's a few lines of code that have given us back that report. Okay, and yeah, 163 fragments which are map-like. So what we can do now is we have built into Wrangler a tool that will help you migrate from dictionary to map. And what we do there, it's nothing, it's very nice, it's automated, but it's not magic. What we have to do is describe, we've got, for example, a client here of dict, and there is dict itself. We modify that. We've got a different API for map, so the things don't fit any longer. What we do is we define an adapter module, and what you do that, and what our refactorings do is fold that adapter into the client code. So it pushes those changes, so your client now looks like a client of the new code, namely map, rather than the old code, namely dict. So this is the sort of thing we have to write, and it's pretty straightforward, at least on this slide. So is_key over dictionary, you can implement using the is_key function on maps, and similarly for toList and fromList and size. But it does get a bit more complicated because the APIs are not the same. If you want to see if a dictionary is empty, you have to check the size of a map and then check whether that's 0. Fetch is get, fetch keys is keys, erase is remove, store is put. An update has a slightly different interface. We can deal with all those things and fold them into your client code. And of course, you can ship this with your updated API, and we will automatically generate the refactoring to do that so that you can change your code automatically. So you write, or the author of the library writes that stuff, and then you can apply the refactorings, and that will turn that into that, which is written, obviously, to deal with the examples we've got there. Now, of course, we've also given you the report about the things we can't translate, and those you have to do yourself. But at least you've only got to look at 10 uses of the API rather than 173, which you would have had before. So ship the adapter. We will generate refactorings from the adapter, and then you can apply those refactorings to your code. And I could just show that in action if I was feeling brave. Let's just show you. So let me explain to you what I'm going to do. So we or you write this adapter. Then Wrangler can generate from that adapter rewriting rules using our language. We compile the rules, and then from within our refactoring tool or from the command line, we can apply those to do that adaptation. So let me show you that in action. So what have we got here? So here are the adapter functions. Let me just turn the size of that down a tiny bit. You can see these are the things I showed you before. And these are the things you can see at the bottom. Those are the things we couldn't so easily translate. So we need to think more about those, or look at. I think in particular we need to look at how you've used those in your project. We could write some static analysis around those, but for the moment we're just thinking about the API level. Okay, so we've got that, and what we want to do is, let's have a look. What we want to do here is API migration. We want to generate the API migration rules. So this generates the refactorings from our, let's call this refac. What should we call it? Dict to map. Right, so that's generated, and you can see that's generated a set of rules. They're relatively straightforward here, but you can see what they've done is they're matching in a particular form. So it's generated those rewrite rules from that file, and then what we can do is, I guess we should compile that. I'll just do that inside the shell. Okay, and then we can take, I happen to have an example here. We've got this example file, and then what do? I go to API migration, I apply it to the current file, and then I have to say which module I'm using, and that's refac dict to map. I want to commit. Ha! Yes. Whew, that's a relief. So that works. So the effort was there. The developer of the API or the changed API needs to produce the adapter module. We do the rest. And you could just ship the refactoring as part of the Wrangler tool. Okay. So that's that. Well, I've just put in a slide about how you can use Wrangler outside Emacs. So that's there. It's documented in the documentation. The tool is on GitHub, and there's documentation there about how you can use it from outside. You know, if you really don't like using Emacs or Erlang IDE, we'd love to encourage you to move it into your own favorite editor. But if not, if your favorite editor is the Erlang shell, you can use it from there. Okay. So finally, saying a bit about the tool set. What we've got in there is clone detection, so we can parameterize. Because you think, what is a clone? What we're looking for when we're looking for clones are two pieces of code, either expressions or sequences of expressions, which you can generalize, which have a common generalization. Now, if you walk far enough away from any two expressions, they're both generalized by X. So everything in that sense is a clone. But we need to set a number of parameters when we're looking for clones. And I'll show you that when I do the demo. We've also got an incremental version of this, so you can run over large projects. You can just check, have any new clones been introduced since I last did a check? And then we've got automated support for removing clones using the domain-specific language, which I hadn't talked about yet. And we've got some other stuff on developing, on spotting bad smells, cyclic exports, and so on inside project. But let's see what we can do. Okay, so another bit of demo. Let's go back to here. And let's say what we want to do is, it looks to me like there is a clone in here. Loop A and loop B look pretty similar, but they're not the same. You know, loop A calls loop A, loop B calls loop B. They've got different messages there, and so on. They're not the same code, but the shape is similar, so we should expect that we can probably identify those as clones. Let's see if that works. We go to similar code detection. We can either look within a buffer or we can look across a whole set of directories. Let's look just within a buffer for the moment. Now, what are we asked for? And I'm sorry, I don't know any way of blowing this up. I'm not enough of an Emacs expert. We are asked for the minimum length of an expression sequence. How big, do you want it to be 20 expressions or could it just be one? We've got a default value here of 5, but actually in this case I'm going to say 1. So it's the lowest possible minimum. So we're being very liberal about what we accept as a clone. Minimum number of tokens, so just a general estimate of the size. I'm going to stick in 5 here. Because this is a small example, I'm setting the thresholds relatively low. Minimum number of times it appears, it just has to appear twice. The next question is perhaps the least obvious. Maximum number of new parameters introduced when you do the generalization. That's effectively how many places these things differ. And what I'm going to say is, let's say 4, which is the default. And then we do a measure of similarity. So we measure how similar the generalization is to the instances of which it's a generalization. I'm just going to say the lowest possible value, 0.1 here. Actually, I'm going to close that. Oh, and let's do it again. Sorry, there's something going on here which I didn't quite understand, which is Emacs. Let's just do that again. Detect code in similar code in buffer. So we want to have 1, we want to have 5, default, and 0.1. And you can see that what it's done is it's detected that this receive statement, one statement, remember, it's big, but it's only one statement, is a clone, and it's generalized in 4 different ways. Over that variable there's the message it sends there, the target of that message send, and the final output in that timeout. So what we've got there is so this gives us, if we want to eliminate a clone, we simply cut and paste. We can cut and paste that into our new library. Now, what we could do then is manually we could aim to eliminate that, but in fact we've built, using our DSL, we have built batch clone elimination, which what this is supposed to do is, Now, what this does is lead us through the workflow of what you do when you eliminate a clone. So first of all, what we've done is we've introduced a function called newFun. Not very helpful, but so we'll leave it as newFun. But it's allowing us to do that renaming. It allows us to rename the parameters because those will be things like message or whatever. So if we say yes, we'll go into an interaction of using those, of renaming those. I'll just say no again for the moment. I'll say no to exporting it. And now what it does is it runs through every instance of that clone in the module. And it says, so we might say yes to that one, and we might say no to that one. And then, if we commit, what we should see is that the first one has been replaced by our new function, and the second one hasn't. And all of that, we have a behavior for these new refactorings we define that allow them to be done interactively, that allow you to gather information interactively, and so on. So we can describe these in a very compact way using our DSL, and so get that behavior just built on top of the simple renaming variables, renaming function, folding a function body against a function call, and so on. So we've got all those facilities there. Now let me go back to my talk. So we've seen that. And as you can see, I've got an example here, and what we did was run through renaming the function, renaming variables. You're given the option to reorder variables if you wish, and then you can add it. You can choose to export that cloned function, and then you fold, interactively decide which clone you want to replace, which you don't. Now, what the point to make is here that what we've written is not just a script. We've got to do something, in the DSL, what we write is not just a script. We have to be able to do some other things. For example, if we're changing names of things, we need to be able to talk about something that was originally called foo when it's been renamed to something different. And that new name may be generated by a bit of program. So we have a way of tracking by their original names entities in the program. We can generate refactoring commands. So instead of saying, for example, we want to rename foo to bar, we can say, because we're in a functional language, and functions are data objects, we can say, here's the function for operating over strings that we use for renaming. And here's a function which will operate over atoms, for example, which will tell us which of those atoms we should apply that renaming to. So we can use these functional abstractions for generating refactoring commands. So we have a high-level description that says, rename like this in everything that meets this test, and then the system generates the actual refactoring commands for us. We have to think about what happens when a refactoring, suppose you're doing A, B, C, and you've refactored quite happily with A, and B fails. What do? Do you back out of the whole thing, or do you carry on and do C anyway? The answer is, it depends. So we have to allow for that control of whether a collection of refactorings is dealt with as a transaction or not. That's with the user. And just to say, we're dealing with pragmatics of how you build these things. There was a huge amount, I think what got us completely sidetracked when we first started thinking about this was, what happens if we do refactoring A and that enables the precondition of B, and we don't have to do that precondition again. I don't care about that. I just want to do the refactorings. And I don't care if I check a condition twice. It's better than checking it no times. So we definitely wanted to deal with pragmatics, not theory, about enabling one refactoring enabling another. So I mentioned this earlier. We can use conditions to say when you refactor it, when you rename, and generate a new name. That's what we did with the camel case example. We have a function that identifies those camel case identifiers, and another function that transforms the names. And we can track names. And then we've got this idea of things being a transaction. And this is the description of what the refactoring you just saw, the composite refactoring for clone elimination, looks like. We call things atomic. What I mean by atomic is it's a transaction. So the whole thing is a transaction. Each of the components has to succeed for the whole thing to succeed. But you can have components that are not transactions. So if, for example, when we're replacing an instance of the code by a call to the function, we fail, we don't care. Just leave the instance there. It doesn't make the whole refactoring wrong. So this can be non-atomic, and this will, so something may fail in there, the whole thing, that stage still succeeds, and the whole sequence succeeds. So we need that fine-grained control of transactionality. And for example, we're doing, at the top level, we do an interactive renaming. We say, we want to do this renaming, you've got to, and the way we describe the refactoring is, this is enough information for us to know to put the hooks into our description of the refactoring, so when we pass that behavior to, when we execute that behavior, we know that it requires us to do some interaction inside Emacs, relatively. And you've got there repeatedly, interactively. So for swapping arguments, you might repeatedly want to do that. and you allow the user to do it repeatedly until they're fed up. So we've got that sort of level of control. So it's a bit like a tactic language for an interactive theorem prover, but has some slight differences on that. I mean, the other point to make is that it's a DSL, so the DSL bits are often realized as Erlang macros. But what's nice is that we can, because it's a DSL that's embedded in a functional language, we can use functional bits like this bit of this closure here, and that, using a list flattened. So we don't. It's not a separate DSL. It's a little DSL embedded in Erlang, and that's a nice. It's one of the nice things you can do. But I just thought it was worth showing that slide to point that out. If you want to find out more about refactoring tools, we wrote a sort of epic thing, which just got in on the ref issue. If this means anything to you, we just got it into the ref, which was a research evaluation thing in the UK. The other nice thing is we had a tour of Stockholm yesterday, and we discovered the Wrangelska Palace. Which was, so there have been Wranglers in Stockholm since the 17th century, and they've even built palaces. More information is available. It's about 10 minutes walk from here. So if you're interested, Count Wrangel constructing his palace, and I'm sure it's been refactored over the years. So if you want to get involved, we're very keen to have people who contribute to the development, contribute your own refactorings to our GitHub repository, and we acknowledge support from the EU through the release project and the protest project. So I'm going to terminate. Thank you.
So guys, if you have questions, please just raise your hand and I'll give you the microphone. Who wants to be brave and ask the first question?
So with this clone detection, Simon, you have to think of these various numbers to begin with.
Well, we provide you with some defaults.
You provide some defaults, but wouldn't it be nice if you just had some sliders that you could drag and see clones appear and disappear? That is, if you could do one run of the analysis and find the whole space and then maybe tell the user, there are clones with the parameter 0.7 at most.
Yes.
And let the user explore.
No, that would be really nice.
Interesting.
That's a good idea. I don't know how you do sliders in Emacs. Right. But you're right. Yes, we could do some guessing and yeah, that's true.
Do you guys have a public library of refactorings? People can contribute.
You can put them in here in our
Just send you a pull request.
Yeah, that would be fine.
Okay.
Definitely.
First volunteer.
Yeah.
So whenever I do refactorings with Wrangler, it changes. I had a float, and it changed from 3600.0 to scientific notation. Why? And can I stop it?
That's a good. We use a pretty printer, so yes, we should talk about that. Yes, we should be able to stop that.
Because it was there for a reason beforehand. So
Okay,
after
fine.
I've used Wrangler, I have to go through and change a couple of parameters, or like one.
Oh, I'm sorry about that.
It's
Send me the
cool.
code, and we'll look at it.
Yeah, I'll do it.
Yeah, do definitely.
Thank you. Next. People down the back never want to ask questions.
For the people at the back, they're always the bad guys sit on the back row. They're reading their email or whatever. Or sleeping, yeah.
So your refactoring of the loop A and loop B functions looked a little bit funny, actually. And I think the reason is that your clones are sequences of expressions, not function definitions. So when you have a recursive function, you end up turning the recursive call into a parameter. Can't you do something about that?
Yeah, that was a bit, yes. Yeah, we should potentially be able to do that. It's unusual that you have a single expression body there. So, yeah, that was unusual. Yeah, I probably had set the parameters slightly wrongly. I'm not selling this parameter thing, am I? No, you're right. I mean, it's odd because they're zero argument functions as well. I think that changes things. Maybe not. No.
So this pretty printer, is it configurable? Because I noticed that it, for example, put a lot of statements on the same line and stuff like that, and it's one code smell for some people.
It is configurable. Yeah, I mean, we're using a standard one, but it is configurable. Yeah. But send me an email with the examples. That would be good.
Would it be possible to use Wrangler to enforce coding standards?
Yes, definitely.
Is it possible now?
Tell us what your standards are. I mean, that's what we have what the code inspection functions do. What I showed you with the finding the non-dict uses of non-map uses of dict. That's precisely what we're doing there. So you can traverse the whole of a project, matching, doing quite complex matching. So you can do purely syntactic matching, but you can do semantics-aware matching as well. So you could do that. Yes.
So it's only a matter of
it's
adding.
a matter of you. I mean, if you can express your coding standards in a reasonably comprehensible way, you know, and if they are reasonable coding standards, I'm sure we can enforce them. We did some of that. We had a project with Erlang Solutions of using the Wrangler code inspection to give feedback on exercise solutions. So you can look for certain sorts of things there. But if you can explain them, I'm sure we can code them. But it would be good to send me an email, and it would be interesting to see what sort of things you're looking for. Yeah.
Yeah, so a follow-up question on the coding standard stuff. What about records, since they are pre-processor stuff? Can you
We do
something
look at
about
things before the preprocessor and afterwards, so in
Okay,
principle
yeah.
we could do that. Yeah.
Going once, going twice. I have one question. Are you doing another talk?
Am I doing another talk? Yes.
This conference?
Yeah.
What are you going to talk about?
I'm talking about the release project. I'm doing an overview of release.
Good.
And then I'm doing a tutorial on Wednesday about a tool called Percept 2.
Right. Is anybody not familiar with the release project? Give us a quick summary, will you? Pitch your talk. I think it's great.
Okay. I mean, the aim was to take the Erlang model of distribution and use that as a way of dealing with massive multi-core systems. So it involves doing things at the VM level, at the language level, some infrastructure, and building some tools. That's
And
my elevator.
Talk is tomorrow?
Talk is tomorrow, I think, same time tomorrow.
Yeah, it's an important talk. All right, thank you very much,
Okay,
Simon.
thanks.